Okay, hi everyone. So we're here with SJPO 2016, question 14. So given that mass M is hanging from the ceiling with length L of a string and is moved in circular motion about this axis of rotation at angular frequency, angular velocity omega, right? Not angular frequency, angular velocity omega. And I asked what's the tension of the string T. Okay, so in this question, let's draw a force body diagram. But in this case, I'm actually going to draw the force body diagram from two perspectives, right? So the first perspective is a side view, and another perspective is a top view, right? So from the side view, we see that it's basically a copy of this diagram over here. Mg as the gravitational force, right, the weight, and T over here at an angle of theta with respect to the vertical. Okay, and so now this is the side view. To draw the top view more clearly, I'm going to actually decompose this T into two component vectors, right? One horizontal and one vertical. Okay, so the red one is the horizontal, and the red in this case is T sine theta, and the blue is T cosine theta. Okay, and another thing I'm going to label is the is going to be the axis of rotation here, and we know that the length over here is L sine theta, right? As seen in the diagram, if the length of the string is L, then the distance to the axis of rotation is L sine theta. Okay, so that we know there's a circular motion about the center of rotation, axis of rotation. So the second case, in this case, the top view, right? I'm going to draw the top view now. The top view looks like this. So the ball is here with mass m, and in this case, the axis of rotation, right, is something like that, right? Is into the page, right? So I can't really see it. I can't really draw a line for it, but yeah, it's this axis of rotation. And in this case, the horizontal, right? If I look from the above, right, then you can see the horizontal tension, the horizontal component of tension, T sine theta, acting towards the axis of rotation, right? But unfortunately, right, the vertical components, right, you can't really see it because I'm going to draw in blue. There's one that's pointing out of the page, and in black, I'm going to draw the gravitational force, right, pointing into the page. But the top view is going to provide us with the picture for the centipede, so for the circular motion, right? So these are the two views, and um and actually all we really need to do is consider top view. So we're asked to find what's the tension in the string. And so if we consider top view, what are the forces acting radially towards the axis of rotation? The answer is T sine theta, and that's pretty much it, right? T sine theta only. Um and so with this net force, you can see that there's a net force acting towards the center of rotation. Pointing towards the axis of rotation. Right, the net force in this case is the force that's going to provide the centripetal force required to keep the object in circular motion. So this is going to be m omega squared, right? R, where R is this length here, but in this case R is actually just L sine theta, right? So this is m omega squared R, but in this case R is L sine theta, and yeah, so actually from here we can actually get the answer, which is the sine theta cancels out, right? Which is, so T is just m omega squared L, right? Yeah, and actually hence the answer is actually A, right? So if you really want to see the side view is just a balance. For the side view, you can just balance the vertical forces T cosine theta is mg. I'm just writing this down so that you can see the two equations is more complete, but actually this equation is completely redundant in this question. Okay, yeah, so that's the tension in the string. So let's move on to question 15.